We've been working with finding the area between a curve and the x-axis. Now we want to look at finding the area of the regions between curves. So here I have two functions, g of x equals 4/3 x plus 1, that's the red line, right? And then we also have the green, which is f of x equals the square root of 3x plus 2. Well, how can we figure out what the area between the two curves is? So I'm looking to find this area right here. Well, we know from what we've done so far, I could find the area under the g of x curve. I could find this whole region by doing the integral of g of x dx from 0 to 3. And I can find the area for f of x by doing the integral from 0 to 3 of f of x dx. And that would give me this whole thing here. So to find the blue, I just have to subtract them. So the area of the green is going to be bigger than the area of the red. So to find the blue, I'm going to have to do green minus red. So I'm doing the upper function minus the lower function. So we can find that anytime we're working with the area between curves, if I find the total area of the top curve, which is this whole green section, and I subtract out the area under that second curve, it leaves me with that remaining. So it always has to be the upper curve minus the lower curve. So here we want to find the area bounded by the graphs of f of x equals x and g of x equals x squared minus 2. So here is my f of x equals x. So that's my first function. And then my parabola is the g of x, which is x squared minus 2. So that's this part. And so in order to figure out how to find my area, I also need to know what are these points of intersection. Now on this graph, I can see that it's from -1 to 2 is going to give me this region between the curves. If it wasn't graphed and I didn't see that, I would have to solve the system of equations to find those points of intersection. But here, to find my area, I can do the integral from -1 to 2. And again, the upper curve, so remember the green is the upper one, so that was x, minus my lower curve, and be careful, you got to subtract the whole thing, x squared minus 2 dx. So cleaning this up, I have the integral from -1 to 2 of x minus x squared plus 2 dx. So I can take my integral, so I have 1/2 x squared minus 1/3 x to the third plus 2x, and I'm evaluating from -1 to 2. So I'm going to have 1/2 times 4 minus 1/3 times 8 plus 4 for my first piece. And then I have to plug in the -1. So then I'm subtracting -1 squared is +1, so that's going to be 1/2. -1 to the third is -1 times -1/3 is +1/3, and then minus 2. And now however you simplify these, you can combine, you can plug that into a calculator. When I go through all of this and simplify here, I'm going to end up with 9/2, 9/2 for my area. In this one, we want to find the area bounded by the graphs of f of x equals sine x, which is our red graph. And here's sine, starts at 0 and goes up. We want to find g of x is cosine x, so that's this purple, I'm going to switch it to green. And if it's bounded by those two regions on the interval from 0 to pi over 2, the area bounded by them is right here and right here. So here we have to break them up because the upper curve does not stay the same throughout the whole interval. So I can see that right here at pi over 4, they're going to switch. So I'm going to do this as two integrals to get my area. So I have the integral from 0 to pi over 4. My upper function here is cosine x minus the lower function sine of x dx. And then I'm going to add to that other area because I'm trying to get that total area. So that's the integral from pi over 4 to pi over 2. But now my upper function is sine x minus cosine x dx. Okay, so I need to integrate. I'm going to switch back to blue. So to integrate the integral of cosine x, is sine x. The integral of negative sine x is positive cosine x, and I'm evaluating that from 0 to pi over 4. And then I'm adding to that, again, the integral of sine x, in this case, is negative cosine x. And the integral of cosine x is positive sine x. And I'm integrating from pi over 4 to pi over 2. So the sine of pi over 4 is radical 2 over 2. The cosine of radical 4 is, pi over 4 is radical 2 over 2. The sine of 0 is 0. The cosine of 0 is 1, so that's my first half. And then I'm adding to that the negative cosine of pi over 4, which would be negative radical 2 over 2. Oops, sorry, I did that backwards. Let me go back. Okay, sorry, I want to start with the upper limit. So the cosine of pi over 2 is 0, negative 0 is still 0, plus the sine of pi over 2 is 1. And then I'm subtracting from that, running out of room, so I'm going to squeeze it below, the negative cosine of pi over 4. Cosine of pi over 4 is radical 2 over 2, so it's negative radical 2 over 2. And then the sine of pi over 4 is positive radical 2 over 2. And so now cleaning up, I have radical 2 over 2 plus radical 2 over 2 is just 2, minus 1. Plus, over here I have 1 minus 0, so we find that this area is radical 2. So here we want to find the area bounded by the x-axis, the y-axis, our f of x equals 2, and g of x equals the square root of x minus 1. So we're trying to find this region here. The problem is right here, when x equals 1, our upper function and our lower function don't stay the same. So we have the same upper function, but up until 1, the lower function is just the x-axis. And from 1 to 5, the lower axis, our lower function, is our g of x. So we need to break this up. Now our first area is just a rectangle, so I can just know that that area is 2. So to get my total area, I'm going to do 2 plus the integral from 1 to 5 of 2 minus the square root of x minus 1 dx. Right, and this 2 is just this little region over here. I could also integrate from 2 minus 0 dx from 0 to 1, but because it's a rectangle, I can also use my geometry. So to get my total area, it's going to be 2 plus, and now here I'm going to integrate. So I'm going to break this apart to the integral of 1 to 5 of 2 dx minus the integral, the square root of x minus 1 dx, again from 1 to 5. So I have my area equals 2 plus, the integral of 2 is just 2x from 1 to 5, minus, and over here we have to do a little bit of a u substitution. So I'm going to say u equals x minus 1, so then du equals dx. So now I have the integral, and I have to change my bounds. 1 minus 1 is 0, 5 minus 1 is 4, of u to the 1/2 du. And remember, you want to make sure you show all of your steps. So here I have 2 plus, 2 times 5 is 10, 2 times 1 is 2, so 10 minus 2, minus, here my integral is going to be 2/3 u to the 3/2, evaluated from 0 to 4. So here I have 2 plus 8, minus, here I'm going to plug in my 4. So 4 to the 3rd is 64. The square root of 64 is 8, so I have minus 2/3 times 8. So I have 10 minus 16/3, which gives me 30/3 minus 16/3 to give me 14/3. Now we can do the same problem slightly differently. So all the ones we've been doing have been dealing with respect to x. We've done everything in terms of x. But I can also look at this and say that I want to do it in terms of y. So if I do it in terms of y, I have this function minus this function, and my bounds are from y equals 0 up to y equals 2. The trick here is I have to write the function in terms of y instead of x. So for our g of x, if I call that y, I have y equals the square root of x minus 1. I need to solve for x. So I'm going to say y squared equals x minus 1. So I have y squared plus 1 equals x. So this is this function right here. So to find my area, I'm going to do the integral from 0 to 2. My top function is y squared plus 1 minus the bottom function is 0. And I'm doing that with respect to y. So we have to be able to do these with respect to x and respect to y. A lot of times one method is easier than the other. So here I just have the integral from 0 to 2 of y squared plus 1 dy. So integrating, I get 1/3 y cubed plus y, and I have to evaluate from 0 to 2. So 2 to the third is 8, so I'm going to have 8/3 plus 2 minus 0. And adding together, I'm going to have 8/3 plus 2, which is 6/3. I get that my area is 14/3. So this is the exact same area that we got when we integrated with respect to x, but my work was a little bit shorter here when I integrated with respect to y. We want to be able to do both because some problems, one method is going to be easier than the other.